Hey guys, welcome back to uh, our energy unit number part 3. I think this will probably be the last part of this unit that we do. In the past, too, we talked about the balance of energy, the fact that um, the kinetic energy of an object is the energy it has when it is moving, and that is 1/2 mv squared. And the potential energy from gravity is equal to the mass times the gravity times the change in the height that the object experiences. And we also said that the total energy initially in any system should equal the total final energy. And from this equation here, we could do a lot of problems, solve a lot of physics problems involving, heights and speeds and masses. Um, this isn't the whole story though, and let me see if I can switch my pen color here. The total energy initially is equal to the total final energy in a perfect system. So the total initial energy equals the total final energy in a physics situation, but not in real life. After an experiment, you're always going to lose some energy here, whether that be to friction or dissipative type forces, right? So your total energy should always be bigger than your final energy, your total final energy. So usually what I put here, if this was a real life situation, is I would say that the total initial energy is equal to the total final energy plus some sort of loss that occurred. But we're not going to jump into that, I don't think, at this point. We just basically say that the potential initial energy plus the kinetic initial energy of our system. So that can be a whole number of bodies. Right now we've only been dealing with questions that have one mass in them, but you could have stuff like hitting each other, two things smashing into each other. And if you're going to look at the potential energy, you got to do it for everything, right? And so I guess I could put a summation here over all of my objects. And then that's going to equal, nice summation notation thing there, that's going to equal the potential final energy plus the kinetic final energy. Okay, so that was the questions we did in the past. We did a Tarzan question where the guy starts at a platform and ends up at a shorter platform and has to swing. And we solved some problems like that. The other thing we did was we said that potential energy due to gravity is equal to the mass times the gravity times the change in height. The other potential energy I wanted to talk about today was the potential energy from a spring. That's my picture of a spring here. Spring potential energy. There you go. And how do we get that? How are we going to get the potential spring energy? And the way we're going to do it is we're going to get the force on a spring. This is called Hooke's law. It's equal to negative times some constant times the stretch in the spring. So K is spring constant. And let's look what units it's in quickly. If this is meters here, and this needs to be newtons, then it stands to reason that your spring constant should be in newtons per meter, so that all the units work out. What's it actually saying when it says newtons per meter? It's actually telling you how many newtons it takes to stretch your spring 1 meter. So a really high number means a very stiff spring that takes a lot of force to stretch, and a very low number, can never be negative though, is a very loose spring like a slinky or something. Okay, So where does this formula come from? Delta x is the, let's say, displacement of the spring from its equilibrium position. So the place where it likes to not move. You know, when a spring is just sitting there like this, and it's not stretched at all, and there's my little object on the spring. Okay, let's say it's a mass or something like that, right? There's my mass. If I pull the string to the right, or the mass to the right, right? Like that, if I pull that with my hand, the spring is going to want to counteract that. Okay, so let's say I pull it delta x. Well, the force on it is going to be in the opposite direction. And that's where this negative sign comes from. So the spring is always trying to pull the thing back into its equilibrium position. So if I stretch it like this, and it ends up there, there will be a force that way on it that wants to pull it back. And if I can press the spring, so I get all the coils tight together and push it to the left, then the spring will want to pull back, push to the left. Okay, so you can compress a spring or stretch a spring. So that's where this formula comes from. It's basically saying my force is just dependent on how far I stretch it. It's linear, so it's not like squared or cubed or anything like that. But there's also some constant there, and it just depends on how strong the spring is. It would be, if this was K was a really, really huge number, it would be very hard to pull the string away from its equilibrium. And that's how like car springs in shock absorbers work in cars. They're really strong springs, and they allow the car to kind of avoid huge bumps by kind of trying to pull the car's suspension back to its equilibrium position. Okay. So there is the force on our spring, but we're looking for potential energy. I'm going to use an analog here from gravity. Okay, so the force due to gravity, Fg, was equal to mg, like that. Okay, and I'm going to put a minus sign here, which means that the force is down for us. Okay. Now, I'm going to tell you right now that the potential energy, and I don't know how many people have gotten this far in calculus. I know I'm not throwing tons of work your way in physics right now, so I don't know what your math teachers are doing, but the potential energy is equal to the let me rewrite this. Hold on a sec here. The force on an object is equal to the derivative of the potential energy with respect to the variable x, or the distance variable. For us, we're just going to say x, or we could say y. I'm just going to say x is this way. Okay, so and it's a negative value as well. Okay, so if I consider that this variable, the change in height, is actually just the variable x, so if this is mgx, let's just make sure this works out. If I take the derivative of a constant times a constant times x, what am I left with? If I take the derivative of mgx, I end up with minus mg. So that worked out for this problem here. The force is equal to the derivative of the potential energy with respect to x, and that is equal to mg. G. Okay, so if I go over here and I say I need a function, this is my potential energy in the spring, what is that going to equal so that when I take the derivative of it, it will equal minus kx. And I won't put the delta in there, I'll just assume everything like the initial position was 0, so it just doesn't make it as confusing as it already is. So there's my force, and it's equal to minus k times x. Give me a function where when I take the derivative, it gives me this, the negative derivative. Try to convince yourself that it is 1/2 k x squared. So if I take the derivative of this, the 2 will come down and cancel the 1/2, and I'll be left with kx and a minus sign. So yes, it does work. That is the hand-wavy argument I have for telling you that the potential energy inside of a spring is equal to 1/2 times the spring constant times the amount that it's stretched squared. This is good too because it doesn't matter if I stretch x to the left or to the right, I still always get a positive number for my potential energy. I should always be storing energy in that spring as long as I'm stretching or compressing it. Okay, so let's look at a couple questions where we're going to use this spring force, for instance. Let's say, example, I'm on this spring. Okay, I've got some mass on this spring, some sort of projectile. Okay, and I'm going to launch it up in the air. Okay, in order to launch, let's just give it a small mass, a 0.08 kilogram mass with a spring, and I'll write the k constant in it. I'll just say it takes 200 newtons to stretch this thing a meter. 200 newtons per meter. So in order to launch a 0.08 kilogram mass with a spring at a max height of, let's say, I don't know, 2 meters, comma, how much will the spring need to be compressed? So that will be part A, I guess. And then part B will say, what is the speed of the mass when it leaves the spring? Okay, so a few things we'll have to do here is we'll have to, one thing we have to do is we have to set this as, like, let's say this is the equilibrium position of the spring. I'm just going to set this as my height of 0 meters because I don't know how long the spring is. The question doesn't really tell me, and it's not super important. All of my answers will be based on the equilibrium position of the spring. The ground can't really play a role in this instance because I don't know like how big this spring is, how long the actual spring itself is. Okay, so that's one thing I usually just ignore in a lot of these questions that are trying to launch things straight up. I just kind of ignore the length, how long the spring is. I mean, if it was 20 centimeters, we'll just add 20 centimeters to our final answer anyways. So it's not super important that we add in all these like tiny little details. The whole point is we're going to try to push the spring down, okay? And then what's going to happen when we let go is it's going to, the force of the spring is going to push this thing back up, right? And probably about the time that the spring reaches back to its equilibrium position, this box will be flying through the air. So we'll quickly take a speed measurement at that point, right at that instant, and then we'll wait for it to reach the top of its arc. So it's going to, travel up. We'll take a measurement here of all our energies and figure out how high it is up there, and that's what we'll do. So what we just want to do in these questions is just say that the initial energy equals the final energy, except we have some springs in here instead of just gravitational potential energy and kinetic energy. So let's look at the initial energy when that spring is compressed. So I will say that I'll have initial potential energy, initial kinetic energy, and initial spring energy. I just write a picture of a little spring there. And that will have to equal the potential final energy plus the kinetic final energy plus the spring's final energy. Okay? So let's go through and see what's going to be 0 right away. The potential energy I'll set to 0 because it's kind of around that equilibrium position. I mean, it'd probably be a little less than equilibrium position because I'm pushing it down. But like I said, I don't want to get into a situation where I'm adding all these tiny little distances. I just want the overall idea of the question to be that the initial potential kinetic energy equals the final potential kinetic energy. I don't want all these like tiny little details where we're going to have to do calculus because the thing's changing in time or something crazy like that. Notice how there's no time in any of these questions anyways. They want to avoid difficulty. Is there any kinetic energy at the beginning of this problem? No, it's just sitting there ready to fly off. And then yes, obviously there has to be some sort of energy in this system. For us, it is 1/2 times k times delta x squared. And we don't know that number. Okay, so that's what we're looking for. The potential final energy is going to be mg times 2, which is our height. Okay, so mg times 2, which is my height. And the final kinetic energy will be 0, and the final spring energy will be 0 as well. So there's no, the thing is not moving at the top, right? At the top of its arc, it should have been stopped and then heading back down to Earth. And also the spring, the mass is no longer attached to the spring, so I don't care what the spring's doing, there's also 0 energy. So the question just boils down to 1/2 k x squared equals mg times 2. So really easy final result there, and we could solve for delta x, which will just be end up equaling, well, I'll just do the math right now. I'm going to do 0.08 times 9.8 times 2, my calculator, that's this stuff, right? And I'm going to times it by the 2 here, and then I'm going to divide by k, which is 200, and then I'm going to square root that answer. And it worked out to be 13 centimeters, or 12.5 meter, or 0.125 meters. So there you go. I didn't have to stretch it that much to get the thing to launch in the air. Part B says, what's the speed of the mass when it leaves the spring? So what you could do with this question is, again, the only energy on the thing is the k delta x squared, and the only final energy is the 1/2 mv squared. Okay, because the second it leaves the spring, it no longer has any spring energy on it. It's still at a height of 0, so it doesn't have any potential energy. And so the 1/2 will cancel, and I will solve for v, right? So I will say delta k x squared over m equals v squared, solve for v, and you'll get the maximum speed just as it leaves the spring. So I get 200 times 0.12 squared. I'm just using my delta x from the previous question, and I'll divide that by the mass, which I said was a small mass, 0.08 kilograms. I'll square root that, and the speed is pretty slow. It's like 6.25 meters per second. Actually worked out to be like a really neat number, and I think it's because I have squares on both sides. Okay, so it worked out to be a fairly clean looking number. All right, so that's all there is to those questions, just like one extra little added difficulty. And if we were in class, we'd be doing a lot more challenging problems with all of this stuff. But today, I just want you to try this question, see if you can do it. Actually, you know what? I'm going to leave some questions for you from the textbook first to see if you want to try them. And they are on page 208. Number 3. Number 4. Number 7. And number 8. So try those questions and brush up on your physics a little bit. We'll probably have a small unit quizzy testy thing next week. I'll post more about that on the Google Classroom. And so stay tuned for that. We're going to do a momentum unit, and then we'll do a special relativity unit as well. Who knows, maybe we may even be back in June, guys. Cross your fingers, because I'm home with a 3 and a 5-year-old all day, so I would love to get back to that school, as a matter of fact. Okay, so we'll talk to you soon. Bye-bye.